Section 5.3 is on standard deviation, and standard deviation is a measure of dispersion or scatter of the data values in relation to the mean. It represents the average distance that a piece of data is from the mean. A low standard deviation indicates that most values are close to the mean. Most data values are close to the mean, which is the data is more clustered or more consistent. And a higher standard deviation means that most data values are scattered further from the mean, and that usually means that the data is less consistent. Unlike the range, the standard deviation considers all the data. Range can be influenced by one extreme value and does not provide information about the variation within the data values like standard deviation does. Right, the symbol for standard deviation is this symbol right here, and the formula is this messy looking thing down here, which looks kind of scary, but it's not really that bad when you break it down into its parts. Basically what you have to do is calculate the mean for all your data, then subtract the mean from each data value that you have, and square each of those numbers, and then you would find the mean of all these squared values, and then take the square root of this number. So if we go back up to the formula, this symbol right here that I'm circling now just basically means the sum of all the data values, the difference between the data values and the mean. When you take all those, you add them all up. That's the sum of all those squared numbers. Alright, so let's just try to do an example, but first we'll just explain to you what we do to help us organize our information when we're doing calculating standard deviation. And we usually do it in a table format. So the first column of your table would have all your individual data values, and then you would take each of those data values and subtract the mean, and then you take that value that you got when you take the mean from each data value, you'd square that and put those numbers in this column. So then to find the standard deviation, you basically just take the mean of all the values you have in this last column here, and then take the square root of that mean, and that'll give you the standard deviation or average distance that a piece of data is from the mean. An example. So the first one says the heights of the Holy Heart basketball team are 182, and these would be in centimeters, 186, 194, 194, and 214. So I'm just going to say in centimeters. So the mean of that data would be to add up 182 plus 186 plus 194 plus 194 plus 214, so add those up and you'll get 970 divided by 5 pieces of data, which gives you 194 as your mean. So then down here in the table you would have each data value, 182, 186, 194, 194, and 214. So in the second column you would just take each data value. So for the first one it would be 182, subtract the mean of 194, and you get negative 12. And then you square negative 12, so negative 12 times negative 12 is 144. And then the next one is 186, take away 194, the mean, and you get negative 8. And negative 8 squared is 64. And 194, take away 194 is obviously 0. 0 squared is 0. Same thing for this one. And then 214, take away 194, is going to be 20. And 20 squared is 400. So then you take all of these values here, and you find the mean. And that would be 144 plus 64 plus 0 plus 0 plus 400. So it's 608 is the sum of all those data values, and there are, even though there's 2 of them that are 0, they're still counted as a data value. So there's still 5 pieces of data. So you divide that by 5 and you get 121.6. So therefore the standard deviation is equal to the square root of 121.6, which is about 11.027, or approximately 11.03 centimeters. Okay, question 2. This is a chemistry teacher has 2 chemistry classes. She gives the same test to both classes. Examine the mean mark for each of the first 5 tests given to both classes and compare the results for the 2 classes. Then determine the standard deviation for each class and interpret these values. So the first one, mean for class A, would be 94 plus 56 plus 89 plus 67 plus 84, which would be 390, is the sum of all the data values in Class A's tests, and that's 5 of those data values. So 390 divided by 5 is going to be a mean of 78 for Class A. And then if you take Class B's marks of 84 plus 77 plus 76 plus 81 plus 74, that's 392 divided by 5 is 78.4. So the averages for both classes are similar. So if you look at the mean, there's not much difference between the 2 classes. Class B seems to have a little tiny bit of a higher average, a little bit of an increased average, but not in comparison. They're both very similar. If you look at the data, though, want to know a little bit more about how the data is dispersed, you can look at calculate your standard deviation. So we have to take the data for Class A and for Class B and calculate the standard deviation for each one. So the first one, just have to go back and write the data down again. Class A was 94, 56, 89, 67, and 84. And the mean we said for Class A was 78. So 94 take away 78 was 16. 16 squared, 256. And then 56 take away 78 is negative 22. And then you square that and you get 484. And then 89 take away 78 is 11, and squared is 121. 67 take away 78 is negative 11, squared is 121. And 84 take away 78 is 6, squared is 36. So if we take this entire column here now and find the mean of that column, we would add up 256 plus 484 plus 121 plus 121 plus 36, and we get 1018 divided by 5 for a mean value of the squared distances of 203.6. So therefore the standard deviation is the square root of 203.6, which is 14.3 approximately. Class B, we had an average from the last page, or mean of 78.4. And so if we fill out our chart for Class B, the data values were 84, 77, 76, 81, and 74. So if you take each data value, 84 minus 78.4, we get 5.6, and then if we square that, we get 31.36. 77 minus 78.4 is going to be negative 1.4, squared is 1.96. 76 minus 78.4 is negative 2.4. Squared is 5.76. 81 take away 78.4 is 2.6. Squared 6.76. And 74 take away 78.4 is negative 4.4. And you square that, and you get 19.36. So then taking the mean of this squared column would be 31.36 plus 1.96 plus 5.76 plus 6.76 plus 19.36. And I'm getting a total of 65.2 divided by 5, which is 13.04, and therefore this standard deviation would equal the square root of 13.04, which is approximately 3.6. So the standard deviation for class B is a lot smaller, which means that the data in B is a lot closer together or consistent, and you can just see by glancing at the numbers that are in class B's data versus the numbers that are in class A's that is true. There's a little bit more variation in class A's test scores rather than class B's. So our interpretation of the results would be that since class B has a smaller standard deviation, class B's results are more consistent. Than class A's. Alright, question 3. Is it possible for a set of data to have a standard deviation of 0? And the answer would be yes, if all data values are equal. Because if all the data values are equal, then the mean would equal that same data value, and therefore there'd be no distance between each data value and the mean. So the standard deviation should be 0. Question B, is it possible for the standard deviation to be negative? And the answer to that would be no, since the average, if standard deviation is the average distance that a piece of data is from the mean, then distance is considered positive, right? So you shouldn't have a negative standard deviation. Question 4 introduces an example where you can use a graphing calculator. The statistics option on the graphing calculator, you can calculate get the calculator to do the standard deviation, because you know that when you're doing sets of data for standard deviation, if it's a large set of data, it can be really tedious and time consuming. So if you've got a large set of data, or even a small set, and you want to just check your answers, you can use the graphing calculator. So there's some steps there to show you how to do that, and you can follow those if you have a graphing calculator. Okay, this next example has, in the tables there, you see that the first column are your pieces of data, And the second column represents the frequency for which each of these pieces of data occurred. So you would not actually have 7, 8, 9, 10, 11, 12 as your only pieces of data. It would be 1 7, 2 8s, 5 9s, 4 10s, and so on. So there's actually 20 pieces of data, and the same thing for this, there's 20 pieces of data. So you can have to take that in consideration if you're doing this by hand, but if you are doing it on a calculator, it's fairly quick because you just do the same steps as we talked about in the previous page, but this would be put in list 1, and this set of frequencies would be put in list 2, and when you do your one variable stats, you just follow it with L1 comma L2, and it would take into account these frequencies and give you the appropriate statistics that you need. So you can try those questions on your own, and the next 2 pages also have some practice questions for you to try and some questions in the book that you can try on pages 262 and 263 of the text. The answers will be posted on Schoology for you to check if you want to see if you got them right. Two pages of this section are just practice for you to try. You can try them either manually or with a calculator, but actually no, the first one you got to calculate it by hand, not using technology. The answers for you to check if you want. For the first one, just try it, but you should get a standard deviation, I believe, for the Lakers should be 9.6, and the standard deviation for the Celtics should be 10.1. And therefore the standard deviation of the Celtics, since that's a little bit bigger, would show that there's more variation in their data. And this last example here, if you do this, then that's another exercise for you to try on your own, but if you calculate it, you should get a standard deviation for year 1 of 6.8, I believe it is, and for year 2 you get a standard deviation of 3.96. So again, if you were looking at which one would be more consistent, it would seem that the year 2 would be more consistent because the standard deviation is smaller. As for the mean, for year 2, it would be 12.6. The median for year 2 would be that those data are already in order, so the median should be 12.5. There would be no mode, and the range would be 18.2 take away 7, highest minus lowest piece of data, which is 11.2. And for year 1, it would be, just calculate, the mean would be 10.8, and the standard deviation would be 6.8. I already gave you that, sorry. The median, I meant. The median would be 11.4, and the mode would be, there would be no mode again because there's no data that occurs more than once there. And the last one was the range, so the range would be 18.6, I'm sorry, is the highest piece of data in year 1. Subtract the lowest piece is 2, so that would be 16.6 would be your range. So those are some for you to try on your own, but those are the answers if you need them.